Question 5, here we go. I did announce it, you're going to get a Punnett square. It's a question of which one, if it's going to be a sex-linked, if it's going to be a simple, pure, dominant, recessive, or if it's going to be co-dominant, or if you're going to get your dihybrid. So here we go. This one has literally got the whole lot in there. It gives you the lovely background of Mendel's investigation, and it gives you tall plants versus short. For this one here, it's really lovely. It gives you suitable letters to use, and purple flowers versus the red flowers, the lowercase always being for the recessive. And for you to think through is if both plants, and it gives you the scenarios, if both plants are heterozygous, what do you get? Based on the laws, state the phenotypes and ratios you would expect in the offspring following across between these parents. If you want to draw yourself up that little Punnett square, this is a simple monohybrid Punnett square, where you just need to think through, hold on a second, what do we get? If both parents are heterozygous for height, phenotypes and the ratios we should be getting, and if both plants are heterozygous for height and flower type. So in a second, the first one is a monohybrid. This is kind of getting you to think that's simple monohybrid. What do we get out of a heterozygous cross? You can't get your 9 to 3 to 3 to 1 ratio there. That's your simple 3 to 1 ratio here. This one here, if you've got heterozygous for both, that was your 9 to 3 to 3 to 1 ratio. So for that one here, what do we get if we're just looking at the height? This is not including any other characteristics. It's only looking at the two alleles for the one gene, which is for height. So the first one, you've literally got 3 tall, 1 short. That is it. For the second one, because you're looking at 2 genes and the 2 alleles for your 2 genes. So 4 alleles in total, but you need to have 1 of each. So what do you get? Your 9 to 3 to 3 to 1. This could be, if you wanted to draw it out as a full-on Punnett square, you can do that. But this is just thinking through, how many tall purple would you get if you were to have that combination of the capital T and the capital P? How many tall and red would you have, capital T and lowercase p? Going through your 4 different combinations, and then obviously the 2 recessive alleles would give you the lowest frequency here. So your 9 tall and purple, 3 tall and red, 3 short and purple, and the 1 short and red. This is the typical ratio that you would be getting. That was literally what we did with the counting the maize kernels. So, and I don't know how many other scenarios we've calculated through, and we did Punnett square practice on. So that is literally just that one. Then comes the word linkage. Okay, 2 marks. First part is state what is meant by linkage, and then explain why those laws of independent assortments only apply to genes if they are not linked. Definition of linkage is if they're on the same chromosome. If they're on the same chromosome, then they are inherited alongside each other and together, because you're not going to get the metaphase 1, metaphase 2 separation of those genes. There's no independent assortment at that point because they're on the same gene. So expressing that in a way that if they're on different chromosomes, then the independent assortment phase can happen, the sort of metaphase 1 and 2, where, yeah, as per earlier question. So linkage, genes on the same chromosome, they can only segregate separately if they are on different chromosomes. Otherwise, that would not be happening. Moving on to the next question here. Here we go, corn on the cobs again. Oh, they look very much like ours, just without the plastic wrapping over the top, isn't it? And you have got given lovely letters given to you. Don't rely on that. They may give you a scenario where you have to come up with your own letters. We've had questions like that. It's giving you the capital A for purple and the lowercase a for the yellow as recessive, and smooth being dominant as a B and wrinkle as a B. Whatever letters it gives you, just run with those letters. They're easy to identify the capital from the lowercase from. Please, 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 the word phenotype is the appearance, the what does it look like. The word genotype is what does it genetically have. So which A, B, 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 A, B, B, A, B, B combination does it have? And careful, It should here actually maybe say gamete genotype, but it doesn't. So initially think through parent phenotype. So how do we find out phenotypes resulting in these phenotypes being inherited? What information does it give you? Okay, the phenotypes, okay. Heterozygous for both color and seed. Okay. Cornucops were produced by crossing plants that were heterozygous, and then you get your F1 generation who are all over the shop. And what does it say here? Show how the different genotypes resulting in these phenotypes who could have been inherited. So parent phenotypes, if you know they're heterozygous for both alleles, then they have to have capital A, lowercase a, capital B, lowercase b, but that's the genotype. Phenotypes is what they're looking like. The phenotype is the appearance. So you're going to get the purple because that's dominant, and you're going to get the smooth because that's dominant. The genotype is where you're going to express the capital lowercase, capital lowercase. Okay, we go purple smooth with purple smooth, capital lowercase, capital lowercase, capital lowercase. And then for the gamete question is what possible combinations are you going to get to put the haploid information into the pollen or into the ova? The haploid information is one of A, one of B. Doesn't matter which one, you need all combinations. So you could have a capital A with a capital B, a capital A with a lowercase b, lowercase a with a capital B, lowercase a with a lowercase b, as per this line here. Okay, and that needs to be there for both to be getting that mark. So on that line for both your parent organisms, you've got some space for your Punnett square, and from there identify which ones you've got. It doesn't specifically ask you to draw the Punnett square, but it kind of implies you're meant to get to, hold on a second, what genotypes will you get a purple and smooth? Wherever you have got the capital A and the capital B, where do you get a purple and a wrinkle where you've got a capital A or you've got a lowercase b? Following on that thought process, have a look here at how this has been filled in. By the way, pause this video wherever you need the mark scheme on the right page. Might as well just stick it on pause. Okay. Does it ask you to draw the Punnett square? No, you can do this without the Punnett square. If you have got it in your head and you don't need this space for the Punnett square and therefore getting the ratios for later on, that's cool. That is cool. Right, phenotype, here we go. That is automatically, I'm thinking, here we go. This is my observed now, isn't it? This is my observed number, so chi-square, maths coming up. The phenotypes of a sample of 400 seeds were recorded. Here are your observed numbers. It doesn't use the word observed. You need to kind of click in. That is, sorry, this entire table is your observed numbers. And you need to come up with the expected yourself, looking at 400 and what ratios you should be having to get, I think we did this before, divided by 16 and get into your 9 to 3 to 3 to 1 ratio from there. Initially, what is your null hypothesis? Your null hypothesis is always that there's no statistically significant difference. I can't say that wording more often. You will have heard me say that so many times. No significant difference. You see, I would have been a bit harsher than the mark scheme here. I would have expected the word statistically significant there as well, and it needs to be between your observed and expected. So there will be no statistically significant difference between your observed phenotypes and your predicted phenotypes as per genetic ratios. And it's lovely. This paper is actually so lovely. It gives you a grid. Some papers don't do that. It gives you the equation broken down. Some papers don't do that. So luxury here. Don't rely on it. It might not happen. You will have to get your numbers for your expected to total up to 400 and dished out into your correct ratio of 9 to 3 to 3 to 1. You can do this literally empirically and just kind of, if I times it by 2, by 3, by 4, by 5, what do I get? But it won't help you. If you add 9 and 3 and 3 and 1 up, you get 16. Divide your 400 by 16, gives you your number for the 1 equivalent. That number times 3 gives you those two. The original number that you've had, 400 divided by 16 times 9 will give you this number here for the smooth and purple. So where are we in the mark scheme? You've got the numbers here. for you to dwell on. I literally divide by 16. If you don't know why 16, go back to, you've got 9 to 3 to 3 to 1. 9 and 3 and 3 and 1 added together gives you 16. So all your possible ratios, numbers in the ratio are there. From there, it should literally be mechanics. Just don't fall into traps and do silly mistakes, and double check your handwriting. If you can't read your handwriting, no good, no good. You need to be able to read your own handwriting. Observed minus expected, square that. At that point, you should have only positive numbers, divided by the expected. So by this column here, divided by your expected numbers, and tally them all, add them all up to get to your sum. That will give you your chi-square value. The mark scheme is actually quite lovely. So you've got the table here, have that against your numbers and see if you went wrong somewhere. Where did you go wrong? You should get your 7.36. I can give marks for parts of the pathway. So at no point, don't do it if you think that, oh, I can't do this at all. At least do part of it. Your examiner will be able to give you parts of it in their mark scheme. And your follow-on question here, and that's actually quite lovely because you've got the probability table, and it's asking you, use your calculated value, your 7.36, and whatever you can read out of this table, and you need to be in the right column, we need to get to that, to explain this conclusion. 5 marks means you can get marks every step along the way. Explain the maths that you're doing. So many of you did not explain, and automatically, okay, I'm circling the right number. I'm in my 0.05 probability, and what's my degrees of freedom? I've got 4 different outcomes. It's going to be my 3 degrees of freedom. Here we go. That's where I am. But not explaining the step. How do you get to it? So I will, obviously, if you've circled it, I know that you've identified the correct value there. I'm on the right one. Here we go. So your critical value, identify. You've identified the 7.82. That is lovely. How do you identify it? In science, we always have the probability. If 95% of your values go into correct, then we say it's not statistically different. If they're out of that value, the 0.5 is there. Your degrees of freedom was your total number of outcomes minus 1. Or your alternative methods, or the alternative ways what you could have had. You would have had a corn on the cob, seedling, a kernel anyway. What other options of having that kernel would you have had? So 4 take away 1 to get to 3. Explain that in the process. Then comes the higher, the lower. Which one is lower or which one is higher? Your calculated value of 7.36 is lower than 7.82. So from that angle, because it's lower, if it's higher, you have to reject the null hypothesis and accept the hypothesis. If it's lower, you should accept the hypothesis. However, sorry, the null hypothesis. However, the numbers are not very far from one another. They're very close together. So is your significance of your conclusion, is that standing on firm grounds? Not really. Okay. Okay. Accepted with low confidence. Why is accepted with low confidence? To kind of click in, the numbers are close. Mark scheme is wording it and giving you credit for the following. So figuring out that your calculated is lower than the critical value of 7.82. How do you get to this? By 3 degrees of freedom and probability. So you need to actually state it, not just circle it on the table as much as it's correct. I can't give you the mark for saying that you've identified that properly. Closeness, and therefore, because we've got because of that closeness between the critical value and the actual calculated chi-square, we've got a low probability, so the difference is not really significant. That was question number 5.